Greetings viewers. This video will go through Cambridge A-Level Further Mathematics. Syllabus code is 9231. This is the Further Pure Paper 2, variant 4 from the May June 2025 series. We attempt question 4, I think, no, question 5. Like the previous questions are already done and uploaded to the playlist. Question 5 is giving us a expression which we want to use the Moivre's theorem to prove this. So the Moivre's theorem, give a recap. The Moivre's theorem, let's say we have an arbitrary complex number, cosine theta plus I sine theta. This is an arbitrary complex number. We can rewrite it as the exponential form, for which if we raise this number to a power of n, then therefore this also multiplies into the index or the indices rule, right? You can multiply to the index, and then this then therefore carries forward into the cosine and the sine. So we can multiply the power straight into the angle. So since we have a 7 here, we're probably going to use z power 7. So z power 7, we can rewrite it as cosine and sine of 7 theta. Right, we write it like that. And also, we notice that the question is giving us or want us to prove the sine only. So sine is also, you can notice, is the imaginary part. So we want to take the imaginary part of z to the power of 7 also. So we want to find this. And to do that equivalent, we will use the binomial expansion. Right, binomial expansion. So we'll expand the z power 7 manually also. So the binomial expansion nr, r from 0 to n, x power n, y power n minus r. And we're going to expand with this one, cosine theta, I sine theta, power 7. I mean, obviously the 7 term, or there's a power 7 means there's going to be like 8 terms, right? So it's going to be taking a long time to expand so many. So what you need to remember is this thing, the power I, right? I power 1, that's I power 2, that is negative 1, I power 3, that is negative I power 4 becomes 1. And it repeats, the cycle repeats again, and it's a modulus 4, right? The power. So what we need to do is we need to find which of the power of sine, because the I is connected with sine, right? So which one is the odd power only, so that will get, or that will have the imaginary unit is still being multiplied together instead of become to the real part. Okay, so that means we're only going to consider the odd expansion, which first let's do the I power 7. So imaginary parts, let me just write this down. Imaginary parts is odd. Okay, the odd powers. Let's take first I sine theta power 7. Okay, so that's why when r is, r is 0, right? So I power 7. Okay, continue. Then we get r equals to 5. Okay, let's say r equals to 5. So we get, no, r equals to 2. This one is r equals to 0, right? This is r equals to 0. R equals to 2. You get n 7. 7 choose 2 equals sine squared and sine to the power of 5. Yeah, sine power of 5. Power of 5, so it will be just a I. So I will put in front here. Okay, next, r equals to 4. 7 choose 4. Cosine of 4. Sine of 3. And power 3 is a negative I. So I'll have a minus I here. Okay, last is r equals to 6. So it's just a I. 7 choose 6. Cosine 6 theta plus sine power 1. Okay, so just a sine. Yeah, we expand this a bit. I power 7, that will be equivalent to I power 3, so it's a negative I sine theta, sine power 7 theta. Then you have a add I cosine squared sine power 5. And don't forget the coefficient, which is 7 choose 2, 21. Then minus 7 choose 4, 35 cosine 35i cosine 4 theta sine 3 theta, 7i cosine 6. This is what is a add, this is a multiplication. Okay, so it's a multiplied sine theta. Okay, up to here, now this is all the imaginary parts already. And now we're gonna complete the imaginary part of this equals to sine 7 theta, which will be equals to this expression. Okay, I'll just rewrite it without the imaginary unit. Now if you notice here in the what we want to prove is everything is in terms of sine, and we want to get rid of the cosine here, so we're going to use the Pythagorean identity. Cosine squared will be equals to 1 minus sine squared. Okay, so there is a cosine squared. What about cosine power 4? It will be this one squared. So 1 minus sine squared and squared, we should give this expression. Lastly, we have also cosine 6, cosine power 6 to deal with, right? Cosine power 6, it will be cosine squared power 3. So we will have. Okay, now we're going to use all this to substitute back into the equation. After expanding carefully, you should be able to get the exact same expression as what they wanted you to prove. Right, so as long as you expand carefully using the correct expression, then you should be able to get this. Okay, so that's for part A. Now we go to part B. Hence find all the roots to this equation. Now if you notice that here there is a polynomial of power of 6, right? So there will be 6 roots straight away that you will know, because power of polynomial of n order will have n number of roots. So there will be, this is 6 order, there will be six roots. And they want us to form, find the roots in the form of sine q pi, which q is a rational number. Okay, what you can notice is that the coefficients are similar to what we have here. So we're gonna make x also to the same power as sine. So everything we're gonna multiply by a negative x. So to give us the sign also, it will match. So it becomes, or we take the whole thing, multiply by negative x, negative 64 x power 7, positive 112 x power 5, negative 56 x power 3, and a positive 7 x. Alright, now we let sine theta to be equals to x, so that our equation looks more like, or it will look exactly like the thing that we have proved just now. And yeah, this entire expression, we will just, entire expression, we can just replace it with what we have proven, which is sine 7 theta. And from here we can get the principal branch, which principal branch means sine 0 equal to 0, so this will be 0. And it will have, it will repeat every pi, right? Every pi will get a 0. So this will be the solution, where n is an integer. So every multiple of pi, you will get a root, which will be infinitely many number of solutions, because nature of these trigonometric functions, they are cyclic, they are periodic, so they will keep repeating and give you infinite number of solutions. So we just need to pick 6 from the principal branch. So probably we cannot take 0 in this case. We cannot take theta is equal to 0, because if you take what that means, if you take theta is 0, means that x equals to 0 is a root, for which this equation obviously okay, for the equation that we manipulated, the x power 7, yes, this is a root for that equation, but we need to always come back to our original equation, which is in x power 6, and you can see that there is a constant term here, which indicates that the root, or when x equals 0, there is a value of y. So when x equals 0, there is not a root. Okay, the intercept when x equals 0 is -7. So again, I stress this, x equals to 0 cannot be a root. So first, reject theta is 0. So we pick n to be 1, 2, 3, 4, 5, and 6 lah, because we want 6 roots, so you can just get six numbers of n. The way you do this, you can be going to the negative, you can go into the positive, but do it in order lah. Alright, so therefore theta we can have pi over 7, 2 pi over 7, and so on. Alright, and then yeah, we rewrite this as our x. And there we have it. There will be 6 roots for this 6 order of 6 polynomial. Right. Yeah, that's the entirety of question 5. Okay, thank you for watching.